Hi, today I'm very happy that we have Kinfei Mok visiting, so to speak, from Cornell University. A really exciting area that's made possible by two-dimensional materials is the fact that you can peel them off and then stick them together at an atomic or molecular scale to make substances that previously didn't exist at all. And because they're so close that the energy scales for making things happen are pretty high, and really opens up both new types of physics and then new applications that didn't exist before. And so one of these materials, it's interesting that high temperature lubricants are the way to go. Like graphite was the original thing that makes your locks work at night. And things like moly disulfide, you can also buy in a spray can. But these transition metal dichalcogenides, if you make the crystal, you can actually peel them off and assemble them to make really entirely new materials. And the electrons and the holes coupled together to make exotons that, again, haven't been seen before. And so that's what we'll hear about today. I'm very happy that you could.
Hey, thank you very much, Bob, for the introduction and for the invitation to give this a seminar. It's my pleasure. So today I will basically talk about one topic. It's about realizing a dipolar exciton insulator in atomic double layers. Okay, and before I go into the talk, I would like to acknowledge the people involved in this work. We share lab with Professor Ji Shan at Cornell University, and most of the works presented today were done by a postdoc in our group, Li Guangma, and a graduate student, Feng Yuan, in our group also. And we also acknowledge theoretical support from Yongxin Zhang and Alan McDonald from UT Austin, as well as the very high quality boron nitride crystal from the NIMS group at Japan, and also the funding sources. And if you are interested in some more details about the work that I'm talking about today, you can actually look into this archive preprint. Okay, so first of all, I would like to give a brief introduction about excitonic insulator. Okay, it turns out that actually excitonic insulator, the concept is quite old already. It's about 60 years ago, first envisioned by Mott when he was thinking about the metal insulator transition problem. And then later on, the more formal theory was developed a few years later by Kohn and Halperin, 1967 and 68. So the idea of the excitonic insulator is that it's a charge insulating state induced by exciton formation. And basically, where the excitons can spontaneously form, and because excitons are charge neutral, and the system is a charge insulating state. And you can actually view excitonic insulator from the semiconductor side or the semi-metallic side. What I'm plotting here is that the y-axis is the temperature, the x-axis is the energy gap or the band gap of the system. Positive band gap means it's in the semiconducting side, negative band gap is in the semi-metallic side, okay? And what it actually, if we look at the semiconductor side, the excitonic insulator can spontaneously form if the band gap of the semiconductor or the charge gap becomes smaller than the excitonic binding energy. So I'm putting the energy here, EB. This is the excitonic binding energy. When the band gap is smaller than that, an exciton fluid can be spontaneously formed, and we have an excitonic insulator in this green region here. Well, there are actually several candidates of bulk excitonic insulators, and typically they involve an equal population of electrons and holes that are separated in the K space or in momentum space. A well-known example is the 1T structure of titanium diselenide. Okay, and usually the transition to an excitonic insulator, because the electrons and holes are separated in K space, the transition is accompanied by a structural phase transition by some lattice instability or charge density wave formation. And because the charge density wave are usually pinned by the lattice or by defects, there's actually no exciton superfluidity in this kind of bulk excitonic insulating system. And also, it's actually not possible to make an exciton wire to this kind of insulating state, because you just cannot really put electrons to that momentum region and put a contact to electron in that momentum region and put another contact to holes in another momentum region. That is really not possible. So it's not possible to really make an excitonic reservoir for this system. So there's no direct access or control of the excitons, meaning that you cannot really access the control the exciton chemical potential and the density in this system. And so as a result, it's fundamentally challenging to establish the excitonic insulating state. There are spectroscopy evidences, but thermodynamic evidence is lacking, even though many years of research. And there's actually another type of excitonic insulator, which inspired by the idea of forming an electrical reservoir for interlayer excitons proposed by Alan McDonald 3 years ago in this PRL paper. The idea is the following, that you, instead of separating electrons and holes in momentum space, you actually can just separate the electron hole in real space. So in this case, you actually put an electron layer in the top position, and then the whole layer in the bottom position here. You spatially separate them, and they form a dipole, a dipolar exciton fluid. So if you have a spatially separated layer like this, and you can actually make electrical contact to each of this individual layer, and if you apply a bias voltage VB, and that actually would reduce the charge gap of the system. So this is the original energy gap EG of the system. If you apply no bias to the system, then the charge gap is just equal to the band gap EG. But if you apply a bias, the charge gap is reduced by an amount equal to the band gap minus the bias voltage that you apply. So an excitonic insulator can also be formed in this case, that when the charge gap EG minus VB becomes smaller than the bias, than the binding energy of the exciton, or in other words, is that the bias voltage you apply is bigger than the exciton energy, then you can actually spontaneously form an exciton fluid. And I want to mention that the bias voltage you apply here in thermal equilibrium is equal to the electron and the sum of the electron and whole electrochemical potential. And that's actually equal to the exciton chemical potential. Another way to say it is actually that the bias voltage of the entire device is actually equal to the derivative of the free energy of the device with respect to the exciton density. And by definition, this is just equal to the exciton chemical potential. So in this system, the exciton chemical potential is very tunable by just applying a bias voltage between these two layers. And furthermore, you can also add gates to this device, top and bottom gates, and apply a gate voltage that would just change the average Fermi energy of the system and tune the electron hole imbalance in this kind of system. Well, compared to the bulk excitonic insulator, there are several differences in the dipolar excitonic insulator. And already mentioned that the electron holes are separated in real space. It turns out that whether they are actually further separated in K space, they don't really matter that much. And there's no CDW or lattice instability in this kind of a excitonic insulator, because the electrons and holes are separated in real space. And as a result, superfluidity is actually expected. And as I already mentioned, that you can actually put contacts to each of the layers, so you can actually form an exciton reservoir that can continuously tune the exciton density and the chemical potential. And also this dipolar exciton fluid, that each of the exciton has a permanent dipole and they can interact with each other. And the dipolar exciton fluid can support very strong exciton interaction. And we call it the strongly correlated excitons, meaning that the exciton interaction energy is much, much bigger than the degeneracy temperature of the exciton fluid. Well, now in order to realize a dipolar excitonic insulator, I would like to briefly introduce a monolayer semiconductors and their unique properties and how it's connected, how it provides a unique platform to realize the excitonic insulator in the dipolar system. Well, I don't need too much introduction of the monolayer TMDs. This is the structure of the monolayer TMD. If you look top down, it looks like a honeycomb lattice structure, just like graphene, with two sublattices. This is the brittle zone. And interesting part of the electronic structure are located at the K and the K prime corner of the brittle zone. And a simplified band structure of a monolayer of this material, it's just that there are two copies of direct energy gaps located at the K and the K prime of the Brillouin zone for the intrinsic material, then the Fermi energy is located in the middle of the gap. Okay. And one unique property of the monolayer TMDs is actually the excitons are strongly bound in this system. And you can sort of see this pointed out by this paper that for an electron-hole pair lives in the monolayer of material, the Coulomb field lines that's responsible for binding this electron-hole pair, they actually most live outside of the material. They live in this dielectric environment. And typically, we embed the material in boron nitride substrates that the dielectric constant is rather small. It's about 4. And experimentally, people actually have measured the binding energy of this object of the exciton here. And what you can do is schematically illustrated here, that you can actually measure the exciton Rydberg states in this material. You can see the 1s, 2s, and so on and so forth, 3s, 4s states. And then you can infer what the energy difference between the first excitonic energy, the excitonic state, and the band gap of the system. And long story short is that the binding energy obtained by different experiments, and also quite consistent with theoretical studies, is that the binding energy is about 0.4 electron volt, depending on the substrate, of course. But I'm talking about like a boron nitride encapsulated sample. It's about 0.3 or 0.4 electron volt. So that's a very substantial excitonic binding energy in this system. Well, there are a few implications for the very strong excitonic binding in this system. And let me just go back to this graph here. I already mentioned that the application of a bias voltage in the double layer can reduce the charge gap of the system. And an exciton fluid can spontaneously form basically when the charge gap becomes smaller than the binding energy of the exciton. And because of the large binding energy of the exciton, that would mean that actually there is a large energy window given by this formula here, that the bias voltage that is smaller than the energy gap, but bigger than the exciton energy, that there's a large energy window for forming an excitonic fluid or excitonic insulator. Okay. In other words, it's basically that as long as you live in this, as long as your bias is applied within this window, this energy window, and the system is basically consisting of excitons only, there is no free electrons or holes at low temperatures. Another implication for the strong excitonic binding is actually the fact that you can support very high degeneracy temperature for the exciton fluid in the system. And so we look at the 2D limit. So the degeneracy temperature is proportional to the density of the exciton and inversely proportional to the mass of the exciton. In this material system, the mass is about an electron mass. Okay, so in order to maximize the degeneracy temperature, all you can do is really just to maximize the density of the excitons in the system. But there is a limit that how much you can actually increase the exciton density, because you cannot get the excitons so close to each other that they start to see the internal structure of the electron and holes, and they start ionizing each other. So as a result, the maximum density you can put into the system is given by a fraction of the density that is defined by the Bohr radius of the exciton. And the right-hand side of this expression here, it turns out that that's actually exactly equal to the binding energy of the exciton. And as a result, so the maximum degeneracy temperature is given by a fraction of the binding energy. And turns out that this fraction has been estimated by quantum Monte Carlo simulations. It's about 0.5. Okay, so what that means is actually that we have a very large Mott density and a very high degeneracy temperature. And if we plug in the experimental measured binding energy of the system, 0.5 times EB, the maximum degeneracy temperature of this system in principle is actually bigger, way above 1000 Kelvin. So the energy scale, as Bob mentioned at the beginning, is just very large. And of course, that's only the exciton binding energy for the excitons in a single layer material. And now we are talking about the excitons formed in a bilayer materials, electron in one layer, hole in the other layer. And because of the extra spatial separation between the electron hole, the binding energy is reduced. Depending on the separation between the two layers, it ranges from tens of milli electron volt to about 100 to 200 MeV. If you really put them close to each other, it can go to about 200 MeV. And indeed, this theoretical paper by a Fogler and co-workers shown that you can quite easily obtain a degeneracy temperature on the order of 100 Kelvin, as long as the interlayer distance is about, you keep it about 2 nanometer-ish. And then that raises the possibility of realizing a high temperature exciton superfluidity in this system. And so this phase diagram is really for non-interacting bosons, the picture. It turns out that if you have strong exciton-exciton interaction, that can further enhance the effective degeneracy temperature of the system that I will briefly talk about towards the end. Okay, we both our group and also Hong Kong Park and Philip Kim's group attempted to realize these atomic double layers of electron and holes. And I'm actually talking about this is our double layer version 1.0 device. We try to make separate contacts to the electron hole layers and then apply a bias between the two layers, trying to realize that concept. And so when we apply large enough bias, please pay attention on the kind of bias that we have reported on our previous paper. It's about 5 volts. It's just way bigger than the band gap of the system here. And it turns out what's happening in our original experiment here is actually that it's not really an equilibrium exciton fluid. We are creating actually a non-equilibrium exciton fluid. What that means is actually that the exciton density is determined by balancing of the pumping rate from the current, from the tunneling current, and the decay rate of the exciton. And once you have these two rates balanced, the excitons reach a steady state non-equilibrium, and it has a certain density. And we made, even though it's a non-equilibrium exciton fluid, we made an interesting observation that once you actually pass enough tunneling current in this kind of device, the tunneling current actually increases in there's no threshold behavior represented by these blue dots in the tunneling current, but the electroluminescence coming out from this device, the light coming out from this device, shows a very characteristic threshold behavior, and over a very short range, a small range of the bias voltage, you can actually see orders of magnitude increase in the electroluminescence counts. And accompanied by this threshold, near this threshold region, there's also enhanced photon number fluctuations that we can measure the photon number correlation function that is enhanced photon noise here. So all these phenomena are actually quite similar to lasing. That suggests there's development, some kind of excitonic coherence in the system. But ever since this experiment, basically we realized it's a non-equilibrium exciton fluid, and it's very hard to actually interpret the results. So we decided to move on to make our second generation of device that we call it the TMD Double Layer 2.0. So before getting into the structure of the device of this 2.0, let me just mention one problem with our original design of the device is that this is the double layer region we are interested in, right? That they have a spatial overlap of the two layers. But the way we made our first generation of device is actually that the electron and the hole contact, they are separated in real space, and furthermore, they have large contact resistance. And what that means is actually that the contact resistance is actually larger than the junction resistance in this device, and the electron holes in this double layer region just cannot be maintained at equilibrium with the contacts, meaning that the electrochemical potential of the electron is not the same as the contact, or the holes. Electrochemical potential of the hole is not the same as the contact. So we want to improve this. We want to reach really a truly equilibrium excitonic fluid by just improving this device design. So this is the device design for those experimentalists who are interested in. This is a second generation of device. We call it making an exciton contact to the device. And the main difference compared to the first generation is actually that now we put the electron and holes on the same side of the double layer. So basically the device is separated into two regions. One is the contact region here. One is the double layer region that we are interested in creating an electron hole gas. Here they are Coulomb coupled. And to actually make the contacts good, we insert an extra boron nitride layer that increase the spatial separation in the contact area. So basically it looks something like this. And if we apply an electric field using the two gates in this device, then we can actually heavily dope the electron contact and heavily dope the whole contact here. And so we can actually form pretty good contacts in this system. And one more thing I want to mention is that because the boron nitride layer, the boron nitride spacer separating the two layers in the double layer region is so much thinner, this electric field cannot generate any electron hole pairs in the system. And also, one more thing I want to mention is that because the electron hole contacts are on the same side, we can actually inject electron hole pairs at the same location. And so as a result, we can actually form an exciton contact or exciton reservoir. And we can create, as I'm going to show, that we can create equilibrium exciton fluid in this kind of device with density fully determined by electrostatics, not by balancing of pumping rate and decay rate. It's just purely by the geometry of the device and the capacitances. Okay, and we can also estimate the exciton lifetime from tunneling measurement. I'm not going to show the results. The exciton lifetime is very long. It's about a millisecond in this kind of device. So there's a very weak leakage of excitons out of the system. Okay, with this introduction, then I'm going to talk about two things, really. One is about a compressibility measurement and how we can actually determine from this compressibility measurement to really show the thermodynamic evidence of the formation of an excitonic insulator. And after that, then we will talk about, because the excitonic insulator, the fundamental quasi-particles are the excitons, and we'll try to construct experimentally the exciton phase diagrams in this system. Okay, so the main measurement that I'm going to do are thermodynamic measurements, and there are two kinds of compressibility that we are interested in. The exciton compressibility and the charge compressibility of the double layer. So to just make some the terminology straight is that if I say exciton compressible, I sort of mean that it's actually a conductor for excitons. And if I say it's incompressible, then it's an insulator for excitons. And the same for the charge degree of freedom. If I say it's charge compressible, then it's a conductor, charge conductor. Also, charge incompressible is a charge insulator. So the specific signature that we want to look for an excitonic insulator or thermodynamic signature is that we want to look for a state that is exciton compressible but charge incompressible. So that's the thermodynamic signature that we are looking for. How to measure the exciton compressibility? It turns out that it's extremely simple. And all you need to do is really to measure the interlayer differential capacitance between this electron and the whole double layer. And this is showing the schematic for the measurement where we apply a AC modulating bias voltage to one of the layers and collect the displacement current from the other layer, or the charge from the other layer. And the important thing here is that the bias voltage modulates the pair density or the exciton density in the system. And as already mentioned at the introduction, that the bias voltage is obtained by the derivative of the free energy of the entire device, of this entire double layer, with respect to the pair density. And as a result, it's actually just equal to the exciton chemical potential. So very simply, the capacitance of this double layer device, this differential capacitance of the double layer device is simply just equal to the exciton compressibility. And this is the result, showing that there's no excessive electron and hole imbalance in the system. So what I mean is that the electron and hole population are exactly equal to each other. And this is the black curve is the differential capacitance as a function of the bias voltage or the exciton chemical potential. And below some threshold here, meaning that when the bias voltage is smaller than EG minus EB, we have no signal and it's an exciton incompressible state. There's just no excitons in the system. And once you go above this threshold, that the exciton binding energy becomes bigger than the charge gap of the system, then we have spontaneous injection of the excitons in the system, and it becomes exciton compressible, a very sharp onset. And there is a peak in the capacitance that I will talk about more later. And this peak can reach the value about 2 times of the geometrical capacitance between these two layers. And you can also obtain the exciton density from this measurement by just simply integrating the area under this back curve, and that's shown by the red curve here. And by just a voltage less than 1 volt, sorry, we can reach an exciton density about up to 2 times 10 to the 12 per centimeter square. That's pretty high exciton density that we have in the system. So in some sense, this measurement also allows you to obtain the equation of state of the exciton, meaning that the population versus the chemical potential. But in addition to the exciton compressibility, we also measure the charge compressibility of the system. The measurement is slightly different. And what we do here is we try to modulate an AC gate voltage to the top gate and collect the charge from the bottom gate. And this is called the penetration capacitance measurement. It measures how effective this double layer system as an entire object in terms of screening out this AC electric field from the top gate voltage. And the important thing here I want to mention is that the gate voltage here modulates the charge density of the entire double layer, not the pair density, but the charge density. It modulates, in other words, it modulates the electron or the hole density. And one can actually show that 1 over the penetration capacitance that we can measure is roughly proportional to the charge compressibility of the entire double layer, with a small correction of the interlayer polarizability, but that correction is not important for the purpose of this talk. So we can just roughly take it as 1 over Cp is proportional to the charge compressibility of the entire double layer. And this is the result, one result that under zero bias voltage, so that the electron and hole Fermi energy is aligned. And when the Fermi energy is located inside this band gap of this double layer, then we have a large penetration capacitance that we can measure. Basically, this value is roughly given by the geometrical capacitance between the top and the bottom gates, because now the double layer are like just insulators and just cannot screen out the AC electric field. But once you move the Fermi energy by your gate, either to the conduction band minimum or the valence band maximum, then you see a significant drop in the penetration capacitance signal, because now when the double layer is either electron or hole doped, then it can effectively screen out the AC electric field that you apply. And so this two-step, the separation between these two sharp steps can roughly give you the binding at, the band gap of this double layer. It's about 0.7 EV. Well, also, we can, as I mentioned, we can change the charge gap of the system continuously by applying a bias voltage. And indeed, when you apply a bias voltage to this double layer, then you separate the electron and hole chemical potential. Then the charge gap of the system, as reflected by the penetration capacitance measurement, just linearly decrease. And you can see that these two steps, the distance just keeps shrinking as you increase the bias voltage. When you apply a bias voltage to about 0.7 volt, which is roughly the energy gap or the band gap of this hetero bilayer, and the system becomes completely compressible, charge compressible, and just almost effectively screen out the AC electric field almost entirely. Okay. So with all this, let me just summarize with a electrostatic phase diagram that is shown by here, that what we have generated, what we have used is basically to measure the parameters of the device using the dielectric constant of the Bn, the thickness of the Bn. And so to generate an electrostatic phase diagram in these two axes, the bias voltage and the gate voltage we apply to the device. And so let me just, there are mainly 4 regions in this electrostatic phase diagram. And let me just explain each region. And this II region, meaning that both the tungsten layer and the moly layer, they are intrinsic. So there's no electron or hole population in this two layers, then it's formed by a band diagram that looks something like this. And the IN region means that the tungsten is intrinsic, but the moly is N-doped. So the moly is N-doped, shown by this band diagram. PI is the tungsten is P-doped. And finally, there is this PN region that both the tungsten and moly are doped, but they are, one is doped by electron, one is doped by the holes. And so it forms a PN junction around this phase space here. Okay. So we can compare this simulation of the electrostatic phase diagram with measurement of the penetration capacitance in this 2D plot, and also the interlayer capacitance. And let me just get into the penetration capacitance first. We have large penetration capacitance value in this red region, and what that means is actually this is a charge incompressible state, and that's corresponding to the II region here that I have shown. And this is fully consistent with the electrostatic phase diagram we generated from device parameters. And you can see that once one of the layers gets doped, and the penetration capacitance gets small in other regions. Okay. And on the other hand, you can also look at the interlayer capacitance region. you only have interlayer capacitance signal when the system is both electron and hole doped. So meaning that in this PM region, so that's why we only see a finite signal in this PM region here. And outside this PM region, we see a very small signal. And yeah, so all these are pretty much consistent with this simulation of the electrostatic phase diagram. And I hope I convinced you that basically this device really allows you to generate an equilibrium exciton fluid in the system. Then the question is, where is the exciton? And let's look closer into this plot here. And I intentionally drew two white dashed lines here, is that basically the top dashed line here represents the closure of the charge gap. What that means is actually that this red area just vanished at this threshold here, that the charge gap of the system would just go to 0 at this bias voltage about 0.675, 0.675 volt. Then the charge gap is closed. And on the other hand, you can also look at the lower dashed line, that the onset of the exciton injection, meaning that the onset of the interlayer capacitance signal happens about 25 millivolt below the closure of the charge gap. So from this data, what it means is actually that in between this region of 0.65 to 0.675 volt, near this region here that I'm circling with my mouse here, that the system only has exciton but no free charge carriers, or in other words, it's actually that it's exciton compressible but charge incompressible. So as I mentioned, that this is a distinct thermodynamic signature of the exciton insulating state just within this small triangle here. And the difference between these two, the difference in bias voltage between these two white dashed line, then just give you the exciton binding energy of the system. Okay, so for this device is about 25 milli electron volt. We have also done it on another device that with a slightly thinner boron nitride that separates between the two layers. And in this case, the binding energy is slightly larger. It goes to about a 40 milli electron volt. But still, you can actually see that the onset of the exciton injection has a smaller bias voltage compared to the closure of the charge gap of the system. And we can also vary, make many devices and vary the interlayer separation and use the same method and measure the binding energy of the system. And on the right-hand side, it shows how the binding energy of this interlayer exciton, depending on the layer number of the boron nitride that's inserted between the two TMD layer. And as expected, well, for small boron nitride thickness, you can actually reach a binding energy that is more than 100 milli electron volt. But then with increasing boron nitride thickness, it just quickly decays to a pretty small value, tens of milli electron volt or even smaller. Okay, and these are the data points, and we compare to some theoretical calculations, and they deviate from a theoretical calculation. In general, the experimental results just decay faster with distance compared to the theoretical calculation. And one of the things I want to mention why there is such discrepancy is that in the theoretical calculation, they did not consider the presence of the top and the bottom gates in the system. And when the binding energy of the exciton becomes small, the ball radius becomes very large, and the screening of the gate actually comes in, and that's not taken into account by this theory. Okay. All right. So I hope I have convinced you at this point that we have generated an equilibrium excitonic insulator. And in that small triangular region that I have shown in the phase diagram, that there is an exciton fluid, but no free charge carriers. And so next is actually that I'm trying to tell you about how the exciton phase diagram look like in this system. First thing I want to talk about is the Mott transition. And it turns out that you can actually calculate the charge gap from the measurement of the penetration capacitance. And you can actually calculate the chemical potential jump across charge neutrality by just integrating the penetration capacitance with respect to the gate voltage you apply to the system. And what I show here is that the charge gap, delta mu, as a function of the exciton density in the system. And you can actually see that the charge gap or the exciton binding energy at this temperature that is continuously decreasing to 0 to a density about 8 times 10 to the 11 per centimeter square. And the interpretation is that there is a Mott transition happening in the system. As you increase the exciton density in the system, the exciton wave functions start to overlap with each other. And instead of an exciton insulator, in a high density limit, the excitons are dissociated into electron and hole. So it forms a electron hole plasma or a semi-metal in this system. So the density that the charge gap varnish is basically the Mott density. And we can estimate the Ball radius of the exciton at 0 density and calculate the Mott criterion, that the Mott density times the Ball radius squared. We obtain a dimensionless number about 0.4. And I mentioned at the very beginning of the introduction that the quantum Monte Carlo calculation has estimated that the Mott criterion to be about 0.5. And so this number agrees quite well. And I will also want to mention that at 15K or down to about 10K at a temperature that is quite small compared to the characteristic energy scale of the system, what we have observed is really a continuous varnishing of the charge gap of the system. So it suggests that maybe we actually have a continuous Mott transition in this system instead of an abrupt Mott transition. Okay, we can also do this measurement at varying temperatures, right? I have shown you the data at 15K, but we can also increase the temperature. And you can see that with increasing temperature, the density for the exciton to dissociate just monotonically decreasing. Or put it in another word, is that if we fix at a particular exciton density, let's say 4 × 10⁻11 and increase the temperature, the exciton become dissociate at this particular temperature. Maybe it's about, going down here, 4 × 10⁻11, then it vanished at about 70 Kelvin, for instance. And what that means is actually that that's the ionization temperature of the exciton, or so-called the Saha temperature of the exciton fluid. So with all this, then we can construct an exciton phase diagram that looks something like this. The y-axis is temperature, the x-axis is the exciton density, and we always keep a 0 electron hole imbalance. The electron and hole population are the same. Okay, and the T star is the Saha temperature, or the ionization temperature, represented by this y squares. So above this temperature, we have a mixture of exciton and plasma. The system is charge compressible. And so we don't really have an excitonic insulating state above this temperature, but below the T star temperature, we have an excitonic insulating state that the system is charge incompressible. Okay, and also in this graph, I also show the single particle degeneracy temperature, this TD dash line here for your reference. And in this, also in this contour plot, I have shown basically the contour shows the color plot for the interlayer capacitance of the exciton compressibility. And you can actually see a dome for the exciton compressibility. There is a region at low temperature and small density that there is a exciton compressibility peak. And our claim is actually that this reflects the Bose statistics of the exciton. And to understand this, we have to try to understand the compressibility of a 2D interacting Bose gas. So we can actually quite easily calculate the equation of state for the 2D interacting exciton fluid by just using the Bose-Einstein distribution and do an integral. Then you obtain the equation of state that the exciton density as a function of the chemical potential here. The D here is the exciton density of states, which is a constant in 2D determined by the mass of the exciton, which is about an electron mass. Okay. And the G here is the exciton coupling strength. Gn is the interaction energy per exciton. Okay. So G is the exciton coupling strength. And once you take a derivative of n with respect to the chemical potential, you can actually obtain the exciton compressibility of this form. I want to highlight two limits. One is the low temperature limit, that it turns out that the exciton compressibility would just go to a very simple expression. It's just equal to 1/G. And so the low temperature compressibility would just directly reflect the exciton interaction strength in the system. In a high temperature limit, on the other hand, this formula becomes slightly more complicated. It's proportional to the density and inversely proportional to the temperature with a negative x-intercept. If you plot it, plot this versus temperature, you have a negative x-intercept that basically reflects that G is bigger than 0 and reflects the exciton are actually repelling each other because the permanent dipole in the system. Okay, so this is the experimental result. What I'm plotting here is inverse the exciton compressibility as a function of temperature. And you can actually see that in a high temperature limit, it follows a linear dependence as expected from the expression for the exciton compressibility. And we can fit the slope and also obtain the x-intercept, which is a negative number, as I mentioned, that directly reflects the exciton-exciton interaction energy. And this x-intercept is the exciton-exciton interaction energy versus the exciton density. And you can see it follows a very nice linear dependence. And from the slope, we can actually determine the exciton-exciton coupling strength G, or the dimensionless coupling constant, which is G times the density of state GD. This number from the slope fitting here, it turns out that it's very big. It's about 11. It's much bigger than 1. What that means is actually that the excitons are strongly interacting. And for your reference, the GD is about 1 in helium-4, which is already considered a very strongly interacting fluid. And GD is roughly about 0.1 or even smaller for bosonic coatoms. So one thing I want to highlight is actually that the very strong exciton-exciton interaction in the system will favor the exciton quasi-condensation and the superfluidity. What it means is actually that it just really raises the temperature for the quasi-condensate and superfluidity. And let me just go back to the peak now. What I'm plotting here is the compressibility of the exciton versus the exciton density. As I mentioned, in the high temperature limit, is proportional to the exciton density. And that's really on the left-hand side of all these plots here, that the exciton compressibility in the low density limit is proportional to the exciton density. That's actually the high temperature non-degenerate limit. On the other hand, in the low temperature limit, is proportional to 1 over G, and that's really on the right-hand side of this peak. That G increases with density because when you increase the density, the exciton wave functions start to overlap with each other and they interact more strongly. And before they reach the mod density. So that actually accounts for the decreasing exciton compressibility of the system with the increasing density. So what this means is actually that the peak is really separating the high temperature behavior on the left-hand side and the low temperature behavior on the right-hand side. And the peak, actually what it means is really that the onset of the quasi-condensate, that on the right-hand side of this peak, which is shown by this black triangles in this phase diagram, that's actually tracing the peak of the exciton compressibility. On the right-hand side of this, we're really entering into the low temperature limit of this exciton fluid with suppressed exciton density fluctuations. And as a result, we actually get a quasi-condensate at an onset of up to about 60 Kelvin in this system. So the last thing I want to mention is actually that this TP is, you can sort of think of it as an effective degeneracy temperature for an interacting exciton, fluid. It's actually enhanced from the single particle degeneracy temperature by an amount that is actually equal to GD, the dimensionless coupling constant, divided by 2. So because we have GD about 12, it's about 6 times of the single particle degeneracy temperature. So it really shows you that, with a strongly interacting exciton fluid, you really have to compare the thermal energy scale with the interaction energy scale to determine the onset of the quasi-condensate. So towards the end of this talk, let me just briefly mention one last thing, is that because we can actually now measure the equation of state of the exciton, meaning that the density versus the chemical potential at different temperature, we can also invoke the Maxwell's relation to obtain the entropy of the exciton. So what I'm showing on the right-hand side here is the entropy per exciton as a function of the exciton density. And at low temperature, as we get closer and closer to the mod critical point, we see a small entropy peak in the system. And we think actually this small entropy peak is related to the fact that we are getting closer and closer to the mod critical point. And I think to further show this is true, we have to go to lower temperature to see how this entire data would evolve. So this is still a work in progress. So to summarize today's talk, I hope I have convinced you that we have created an equilibrium excitonic insulator that's created an excitonic equilibrium exciton fluid. And we have constructed the exciton phase diagram that shows the mod transition, as well as a thermodynamic evidence for the quasi-condensation up to about 60 Kelvin. This temperature can also be further enhanced if you actually increase the mod density by decreasing the boron nitride thickness between the 2 layers. And the excitons are strongly interacting, and that favors the quasi-condensation and the superfluidity. Before ending, I would actually like to highlight, a few potential interesting directions that can go after this work. One of the things that, what we have shown is actually that we have made a single exciton contact in this device, but there's no reason we cannot make a multi-exciton contact to this double layer region. And so this is a very old idea back in 1967, talking about how you can actually make exciton flow as long as you can make a counterflow of the electron and hole layer. This is one of the very good ways to really prove that there is exciton superfluidity in the system. And I think someone has to do it to show that there is indeed exciton superfluidity in this two-dimensional system.
Okay.
Another thing, this system with a controllable exciton density and exciton chemical potential provides quite an interesting system to study the BEC-BCS crossover under zero magnetic field. And the finite magnetic field version based on Landau levels and quantum Hall regime recently reported by Philip Kim and Corey Dean. This showing well, this is actually a phase diagram showing an atomic system that you can how to go from BCS limit to BEC limit. And I think this is also an interesting system to explore the BEC-BCS crossover in a zero magnetic field limit and also pretty high temperature supposedly. And the final thing, of course, all the interesting ideas these days are related to Moray. And so we can think of maybe we can actually replace either one of this layer or both of the layers by a Moray layer. And then the idea is to really trap excitons in each of this Moray site to form something called the Bose-Harbour model in the system. That's an interesting platform to study more superfluid transition, the supersolids of excitons, the solid phase of excitons, as well as very interesting recent proposal by Ashvin's group on using this kind of platform to realize a chirospin liquid state in the pseudospin space. I should call it chiral pseudospin liquids. So with this, I thank you for your attention and I'm happy to take any questions if there are any.
Gee, that's really exciting results. A beautiful talk. Let's see, to ask questions, please go in Q&A or into the chat, and I'll take a look. Here's a question for Philip Kim, and this says, amazing data, exclamation. Could you tell us more about tunneling experiment that shows 3 milliseconds of electron lifetime?
Oh, sorry, Philip, I don't have any data to show here. I don't have that slide. I should have actually posted that slide. But let me just point you to a, sorry, it should be here. Let me just point you to our archive preprint that we posted on archive 2 days ago. I believe it should be an extended data, anyway, a supplementary figure 3 or 4. There you can actually look up the tunneling current data. That from basically the idea is that from the tunneling current density of this device, which is very small, then you can estimate the leakage rate of the excitons out of the system. And that's about 0.5 millisecond.
Okay, thank you. Another question from Tahi Kim. Have you tried to observe magnetic field effect on the exciton compressibility?
Yeah, very interesting question. And indeed, we have tried. The reason we have tried is because of this idea from Patrick Lee recently talking about the gap oscillation of the excitonic insulator in the semi-metallic limit, not in the limit that I'm talking about. I'm mostly talking about the semiconductor limit. We did see some signatures of gap oscillation in the system, but one thing we really worry about that because we are using graphite gate in the device, and the graphite has quantum oscillations, and because the excitons are really sensitive to the dielectric environment of the system, and the field lines can actually penetrate a little bit into the graphite gate here. So we are actually afraid that that oscillation is due to the graphite. So next thing we really want to show that there's an intrinsic oscillation of the charge gap of the excitonic insulator is to really replace the graphite gate with some metallic gates to really confirm what we have seen. Yeah. So we started looking at this, not conclusive yet. Yeah.
Okay, thank you. Another question. Hi, thanks for the very nice talk, 2 exclamation marks. True. Why is the gap only 0.7 EV in the tungsten selenide, boron nitride,
very
selenide headers? Doesn't the inner lecture exciton have a higher energy than this? Or is it due to the HBN spacer layer? Go ahead.
Yeah. Actually, the reason is that because we actually have to apply an electric field from the 2 gates to make the contact good. So there is a interlayer potential developed between these two layers. And in fact, we actually have measured the gap size of the system, the band gap of the double layer as a function of this electric field. And it follows a linear dependence. And if you extrapolate all the way to zero electric field, it's about 1.6 EV. That is really the interlayer band gap of this double layer system. And again, you actually can go to our preprint here. That it's one of the supplementary figures that we show the measurement of the band gap at varying electric field. So the reason for the small band gap is because we actually have to apply electric field to make the contacts good.
I see. Good, thank you. One from Bert Halperin, beautiful work. Can you comment on the spin and valley degeneracies of the electron hole bands? This should affect the condensation transition density at T equals 0.
Yeah. So the system, because of spin-orbit interaction, there's really a twofold degeneracy left in the system for either the electron or the holes. And so in some sense, the spin and the valley are coupled in this system so that we only have the twofold degree freedom left. Yeah, that I think I hope this already answers the question. So this basically, you can treat it as only with a twofold spin degree of freedom in the system. And another thing I want to comment is actually that a mean field calculation by Allen actually has shown that in some density range, it's possible that the system can spontaneously break the valley degeneracy or the spin degeneracy in this system. We have not seen any signature of a spontaneous time reversal symmetry breaking, maybe because of this order in the system, or maybe our temperature is not low enough for doing this measurement because it's limited by the contacts.
Okay, thank you. Another question from Zayu Hao. If you measure the phase diagram at a point outside the small triangle where the interlayer capacitance remains high, would the phase diagram look very different?
You mean outside this? Yeah, the phase diagram, we are trying to go along this line, always maintain an exactly electron and hole balance. Once you go outside the balance, we actually have not really carefully mapped out the phase diagram, but because you can actually see a hint of the data here that the interlayer capacitance is actually still quite a bit enhanced from the geometrical value, from the geometrical capacitance. What it means is actually that if you have a little bit of electron hole imbalance in the system, the excitonic effect is still important. But I only can say that this is the regime that we really fully understand, the data, that we also have not really tried to map out the phase diagram with uneven electron hole population. But let me also comment on one more thing, is that if you go outside the triangle along this direction, that's really beyond the Mott density. And if you look at the phase diagram here, once you go above the Mott density, actually the interlayer capacitance will just go almost to the geometrical capacitance of the two layers. And that's consistent because now you really have dissociated electron holes in the system.
Okay, thank you. Another question, Huang Zumeng. Thanks for the nice talk. How does the contact resistance go low compared with 1.0 version of the bilayer device?
Okay, let me just go back to the very beginning of here. So one of the, there are two things. One thing is actually that we have not been particularly careful in making our contacts in the first generation of device. We use graphene electrodes. It turns out that platinum electrodes can form much better contact to this material. So that's really one thing. And the second thing is actually that we did not pay particular attention on trying to apply an electric field to really make this region heavily hole doped or heavily electron doped. And that really can also suppress the contact resistance of the sample. And these are really the main advance of the second generation of device. And maybe one last thing I want to mention is that why we really want to put these two, the electron and hole contacts on the same side of the device. We actually have really made, we have made devices that the electron and hole contacts are separated in space. And it turns out that at low temperature, in order to inject the electron hole pairs into the system below the band gap of the system, right? You actually, you have to create a electron hole fluid, or exciton fluid, without creating free electron hole carriers. It turns out that when the electron hole contacts are separated in real space, correlated injection of the electron hole pair is actually not allowed. So we actually, if we make that kind of devices, what we find out is actually that the triangular region here, the interlayer capacitance is 0 at low temperature. We actually cannot inject excitons when the electron and hole contacts are really separated. We need to bring them on the same side to actually get a correlated electron hole pair injection.
Okay, great. Well, this is a phenomenal talk. Lots of nice questions. Thank you so much for visiting us over the web.
Thank you. Yeah, my pleasure.
To give this talk, it's really enjoyable. But thank you so much.
Okay, thank you.
Thank you. Bye.
Thank you.
Bye.
Bye-bye.